My dear friends, welcome back to Be Spice. In this session, we'll talk about safety requirement specification, meaning the specification for preparing the SRS. That is the point. We are not going to prepare the document. We are not going to prepare the document here. Okay. What we are going to focus is the requirement, meaning the specification for preparing the SRS. Okay. If you are on a owner side, okay, operator side, and involved in the functional safety aspects, you may, happen to prepare this SRS. So that is the intent of this session. Okay. So in this session, we will cover the purpose, the scope, document layout, meaning the look and feel, safety integrity level, SIF specification, SIF description, common cause failures, safe state of process, demand source and rate, proof test interval, SIF response time, mission time, and target SIL and achieved SIL. So, friends, this is just part one. Okay, I'm going to cover this in three parts, okay, because of the to give you a concise notes within the 30 minutes slot, so that you will not get bored. Okay, so let's move on. So this is going to be a very useful concept. Of course, there's a lot of theory out there. So we'll cover this SRS in three parts, then finally we'll go to the SIL verification and SIL classification and verification. Okay, that's good. Okay, let's move on. What is the purpose? The purpose of SRS is to identify and present the safety requirement of safety instrumented function. As simple as that. Okay. The purpose of SRS is to identify and present the safety requirements of SIF. Okay. Right. So instrument safeguarding involves all instruments, components, related actions for unscheduled process conditions performed in safety instrumented system. The objective of SIS, as we all know, is to set the process into a safe state, right? If and when it moves out of its operating window towards an unsafe situation. Okay, right. Instrumented safeguarding comprises the protection against the loss of life, serious injury, production loss, equipment, and environmental damage. So this SRS sets the requirement for development of safety instrument system and supports validating that all of the requirements have been satisfied, and support verification activity at all phases. As simple as that. I hope this is clear. So this is a document which we can use for development of SIS and validation and verification. Okay, friends, that's it. So again, this is not the SRS document. This is the specification for preparing the SRS, meaning the contents, all these we are going to discuss. Okay, friends, let's move on. The scope. SRS is intended to ensure that all criteria, philosophies, evaluated and conceived or developed into a descriptive quantification and implementation of for their individual representation. So that is the intent, that is the scope. Okay, friends. So what SRS contains? SRS contains functional design, operational and safety requirement for the each SIF. Okay, right. SRS is a specific requirement of IEC 61508, IEC 61511. So yeah, which define good engineering practices for designing, implementing, validating safety instrumented system. I hope you had watched my previous session on the 61508 and 61511. If not, you can spare some time and watch. In that, we have covered extensively on all aspects of IEC 61508 and 511. Okay, friends? Right. So now document layout. Okay. This, if you see the SRS, friends, it specifies all the requirement of the SIF that have been assessed with the safety integrity level 1, 2, 3, which have to be performed by the safety instrumented system. Okay. So it covers all the safety aspects of actual SIS hardware and software implementation. SRS shall be used during SIL verification phase. That is a very important term. Software and hardware validation phase and during operational phase of the plant to check that safety requirements are implemented in the SIS in its entirety. Okay. I hope this was very simple and clear. Okay. Let's move on. Now, safety integrity level. Okay. Now, the safety requirements of the plant are evaluated based on process hazard analysis. That is a hazard study, right? I hope you have watched my previous session on hazard and LOPA. If you have not watched, because the details were covered there. Okay, friends. So the integrity level of each determined safety instrumented function are classified into a SIL in accordance with IEC 61508 and 511 standard. So the SIL corresponds to the amount of risk reduction that can be achieved with a specific SIF. As you can see here, SIL 1 with risk reduction factor 10 to 100. Okay. SIL 2 with 100 to 1000. Then SIL 3, 1000 to 10,000. Then SIL 4, 10,000 to 100,000. Okay. So this is the general idea about SIL. Of course, the experienced engineers knows this. This particular slide is focused more on what do you call the freshers and intermediate. So basically the idea is this SRS should also cover this SIL aspects. Okay. Here one thing I want to highlight. Higher the SIL rating means more risk reduction that can be achieved. Very important. Just remember, friends. Then few more. In practice, this SIL 4 cannot be achieved. Okay. And is not permitted as per IEC 61511 code for process industry. Okay, maximum we go for SIL 3, friends. Even in a refinery where I worked in a big refinery, okay, as a team leader, I worked actually for 3 years in that. So, in fact, in that refinery also, if you look at the SIL 3, we can it's not that much actually. So we need to try to make it the SIL 3 as low as possible. That was the intent, and we have done it actually. Okay. Just want to share Okay. Okay. In case the determined level is SIL A. Okay. SIL A, no strict implementation requirement. So this can be built in DCS. So if you're, the SIL rating is A, then you can implement in DCS itself. No need to go for safety. Okay. That's a point. Okay. Now, SIF. SIF specification section explains the minimum requirements for various SIS elements under each category. So this SIF is also one part of the SRS. So this refers to the functional and integrity requirements applicable for all the SIF that are having SIL 1, 2, and 3. Okay. Project specific SRS, SRD, rather project specific SRD, safety requirement data sheet for each SIF shall be developed and included as part of the SRS. You got it, friends? So SRS should also have the safety requirement data sheet for each SIF. Okay, right. So each identified SIF is expressed in a general way for easy understanding, okay, by other personnel involved with safety lifecycle activity, including those involved with the implementation, testing, commissioning, operation, maintenance, audit, modification, decommissioning, all these are. So each SIF is identified, is expressed in a general way for easy understanding. Okay, so that is a point. So the description also includes the hazards being prevented or mitigated by the SIF and all components associated with the SIF, including initiator, logic solver, final elements. All these also should be part of this SRS. Okay, friends? Okay. Then what is this? Just one moment. Just hold on, friends. Okay. Let's move on. So here we have discussed about so for purpose, scope, document layouts, integrity level, SIF specification, SIF description. Okay. Now common cause failures. Very, very important, friends. Common cause failures. Okay. So common cause failures result from the failure of more than one component. Okay. I think this is a typo error. More than one component, subsystem or subsystem as a result of the same event or cause. Okay. So this is the point. A common cause failure result from the failure of more than one component. More than one component, subsystem, system as a result of same event. Okay, that's the point. So another point we need to see also the beta factor. So this way you will be discussing that in the verification, SIL verification. So basically, this beta factor is assumed number used in PFD calculation to represent the common cause failure and considered in the range of 5 to 10% in general. Always think in general. Beta factor, we put 5 to 10%. Okay. Just remember, friends, this beta factor. Okay. So, yeah, 5 to 10% actually. Okay. Right. Then the point to take note is that this is not applicable in case of a single trip initiator or final element and applicable only to voted configuration. What is that? 1 out of 2, 2 out of 3 like that. Okay. That is the point actually. Okay. Right, friends. Design techniques to be used to avoid common cause failure. How? But not limited to, separation, redundancy, diversity, peer review, and strengthening of components. Okay, these are the things actually. We can, avoid common cause failure by having a separation, redundancy, diversity, peer review, strengthening of the components. The initiator associated with a particular SIF, which forms a part of any voting group, shall have to be segregated to the extent practical as much as possible in a separate junction box, multi-pair cable, and input module. Hope this is clear. The initiator, like the sensor and the transmitter, associated with the particular SIF, which forms of any voting group, 2 out of 3, that has to be segregated. Okay, in a separate junction box, a multi-pair cable, and input modules. Okay, friends. So this is about the common cause. Okay. So additionally, I also want to give you something. Typical common cause actually, just for your benefit. You can see here, this is the common cause failure. This is the design requirements. For example, common cause failure, electrical. You see, supply power via UPS, all right? Redundant power supplies. Then PLC malfunction failure. SIL3 certified PLC, routing of redundant cables in diverse path, vibration in the surrounding shall be within the allowable limits, all these are. And also air conditioned room to minimize effects of temperature and humidity. Then IO module fault affecting multiple equipment. So we need to have a IO segregation, okay, and controller wise, right? Then, for example, you have a pump A, pump B. Then one IO related to pump A, we can put in one module. Then the other one we can put in the other module. Like that, we have to segregate. Then loss of communication link and impact. For that we have to go for the redundancy or additional logic for right, to redesign the architecture. Then fire in cable tray, cable room. So all field cables shall be fire resistant. So that is the mitigation. IEC 60331. Remember this. Okay. And flooding of cable room. So inclusion of appropriate drainage. Then high temperature and humidity. So for that we have to go with the proper selection of equipment to meet the environmental condition. And of course the air conditioning and proper installation of sunshades. So another point here, where redundant instruments are specified, appropriate common cause factor to be included in the verification process. This is what I highlighted. Okay. Don't worry. Just get to know all the concepts. We will focus on this verification and after, once we're done with the SRS. Okay. Then after this common cause, safe state of the process. See, what is this safe state? So basically, it's a state of the process when safety is achieved, and the same shall be defined for each SIF and shall be included in the SRD, that is Safety Requirement Data Sheet. Okay. Here, action necessary to achieve or maintain a safe state in the event of detected fault shall be described in the SRS. All these actions necessary to achieve or maintain a safe state in the event of a detected fault shall be described. Okay, friends? I hope this is clear, right? Listed are the terms used to define the safe state. What is that? Which ASD valve should be opened or closed? State of operation of any rotating equipment of each event. Okay. The SIF shall be designed to move the process to a safe state on the loss of energy. What is that? Electrical power, instrument tab. And consequently, the logic system is fail safe. Fail safe when power to the process is lost. So this is the safe state of the process, and this needs to be documented. Okay, right. Then the next is demand source and rate. This little bit different actually. See, basically this demand source and rate on each SIF are identified during the SIL classification exercise, meaning the LOPA exercise. Okay. So in that case, we should have, we should be consider both low demand and high demand. Okay. All these we covered in our previous session, friends, in IEC 61511. Okay. You can verify and yeah. Various demand source for a particular ship shall be discussed in detail during the sales study and shall be recorded in the assessment review report. Okay, right. So the assumed sources of demand and the demand rate of SIF and the total demand rate are included in the SRC. So this is about the demand source. Then the next one is a very important one, proof test interval. See, this is very important actually for SIL verification. The required proof test interval value for each element in a SIF is identified in the SRD and shall be applied during SIL verification stage to check the compliance of SIF to the target SIL. Okay. See, normally this is identified in months or years. Okay. Consideration should be given for proper selection of sensors and final element to facilitate online testing. That is very important. Okay. Proof test interval for the sensor, logic solver, and final element are derived with reference to the following. Okay, what is that? For each safety function, there is a perfect proof testing and repair. Okay, right. The proof test interval is at least an order of magnitude greater than the automatic diagnostic test interval. That is the point. Okay. For example, you have a automatic diagnostic test interval that is 6 months. Then proof test we can go for a 1 year. Okay. Sufficient resources are available to work on all common failures, known failures. Okay. Manufacturer recommendation. All these we need to consider, friends. Proof test. In fact, I'm going to cover this proof test in detail actually in a separate session, that is the SIL classification and verification. Okay. Just now you understand this. You see, basically we need to come out with the proof test for initiator, logic solver, and final element, friends. See, typically it's like ranging from 1 year to 3 years actually. This is linked to the annual turnaround actually of a particular plant. See, for example, if your turnaround is only once in 4 years, then you have to go with that actually. Otherwise, you will have a challenge in doing that. Of course, the proof test actually, that period that impact the the SIL rating also. When we do the verification, you understand that. No problem. Let's move on. So this is a proof test. Yeah, this is what I just highlighted. Typical proof test interval for the SIF system, that is initiator, logic solver, and it's sensors, that is 6 months, logic solver, final element, all these. So shorter the proof test might be applied to critical loops at the time of SIL verification if it is allowable as per verification outcome. So that is the point. Take note, friends. Okay, friends, right. So yeah, now we have seen the proof test interval. Okay. So the test procedures are, yeah, the test process, I think we have missed out this, right? A detailed proof test procedure shall be developed for each element for SIF, or generic test procedure shall be developed for all type of sensor and final control element. This is another point actually. A test procedure we need to develop. All these should be part of the SRS. Test procedure should contain a detailed test for effectiveness with measurable pass-fail criteria. Okay, all this format we need to put in place, right? Okay. Test procedure shall also include manufacturer requirements for testing the specific devices with each SIF. Okay, right. All these need to be incorporated, friends. Now, after this proof test, SIF response time. This is also another very important aspect, friends. See, basically the response time requirement for the SIF is to bring the processor to a safe state, okay, and shall be within the process safety time. That is very important. The response time, take note, friends, response time of the SIF to bring the process to a safe state and shall be well within the process safety time. Of course, we need to check with our process colleagues on the process safety time. So, what is the process safety time? Process safety time is defined as the time period between a failure occurring in the processor, that is BPCS, Basic Process Control System, with the potential to give rise to a hazardous event, right? And the occurrence of the hazardous event if the SIF is not performed. Okay, so that is the process safety time. Okay, so process safety time, or the PSD we call it, shall be made available by the process group and shall be recorded in the SRD for each SIF. Okay, so SIF response time shall be less than the process time, as I highlighted. Okay, and typically less than or equal to 50% of the process time. See, for example, process time is 3 seconds. Okay, sorry, 3 minutes. Then we have to go with 50%, like 1.5 minutes, like that, or 4 minutes, or 2 minutes, like that. So to account for aging processor, possible degradation of the response time of the component or the entire life period of the plant. I think this is a typo error, life period of the plant. So the point is, SIF response time shall be less than processor safety time. Okay, and typically less than or equal to 50% of the process safety time. Okay, friends, got it? Right. SIF response time versus process safety time shall be checked, and recommendation has to be made to adjust the SIF response time criteria with respect to the PST is not met. Okay, I hope you also got this. The SIF response time, very important. Okay, friends, right. SIF response time shall be checked, verified during SIL validation process to ensure that the response time of the implemented SIF loop meet the criteria set in the SRT. Okay, that is the point. Very, very important, friends. SIF response time shall be checked, verified during SIL validation process. Okay. What for? To ensure that the response time of the implemented SIF loop meet the criteria set in the SRT. So I hope you got some idea about the SIF response time. Okay. Then few more. Unless otherwise specified for an individual SIF loop with other consideration like opening time of the valve affecting the flare system or closing of the valve causing unnecessary surge in the line, the maximum response time shall be below, as below. You got it, friends? Unless otherwise specified for an individual SIF loop with other consideration like opening of the valve affecting the flare system, closing of a valve causing unnecessary surge, the maximum response time will be as below. For sensor, it is 1 second. Okay. Logic solver, 300 millisecond. Final element, 1 second. So this is the SIF response time. I actually explained earlier in the previous slide like 4 minutes and all, right. So that is actually just for example only put up. Okay. So maybe you can consider 4 seconds, right? Okay. Yeah, process time. So the SIF response time is 50% of the process time. Okay. So here it is 1 second, 300 millisecond. Okay. Final element 1 second. So final element, another criteria here. Final element. For example, body sizes up to less than 4 inch, it is 3 seconds. Okay. So if body size is 4 inch, and it go on increases, then we can consider that as a pipeline equal to the pipeline size. Meaning, see, for example, less than 4 inch, it's 3 seconds. Okay, for 4 inch, 4 seconds. 5 inch, 5 seconds. 6 inch, 6 seconds. Like that, friends. So this is the SIF response time. I hope it's clear. Then another important mission time. What is the mission time? Mission time of the plant is the maximum run of the plant without major maintenance, turnaround and overhaul. Okay. Mission time is the plant is the maximum run of the plant without any major maintenance, turnaround or overhaul. Just I highlighted, right, the maintenance 4 years. So in that case, if 4 years is your turnaround, and within 4 years nothing happened and no major maintenance turnaround, then that is your mission time actually. Okay, so this time could vary from 5 years to 25 years based on the design lifespan of the plant. Okay, so it is considered that once with each mission time period, the SIF components are subjected to repair, recalibration, retrofit and restore to full condition. Okay, this is the mission time. So that is also we need to cover here. Then achieved. Now achieved and a target and achieved SIL. This one we have covered earlier, but just want to tell you. See, friends, target SIL is the safety integrity level required for a particular SIF as determined and recommended during the SIL classification exercise. That is during the LOPA exercise. Okay. So this is the target for a particular function which needs to be collectively met. This is actually a typo error again. Met by the individual elements performing the particular safety function. Okay. So achieved SIL is the safety integrity level that is calculated for a particular SIF which is determined during the SIL verification. Okay, that's a point. Target SIL, always remember LOPA, SIL classification. Achieved SIL, always remember verification. Here what we do, target SIL, for example, SIL 2. Oh, okay, that is a target SIL which we achieved during the LOPA. Okay, then we need to see whether that is, okay during the SIL verification exercise. Okay, so both target and achieved SIL for each SIF shall be included in the SRD. So that is the point. So during SIL verification, it has to be ensured that target RRF, this is a risk reduction factor, friends, indicated in the SRD is achieved by the SIF components. See, like as I highlighted, SIL 2, okay, then during verification, we have to see whether the target RRF is achieved by the SIF component during the verification. If a target RRF is not met, then the SIF components are to be redesigned, modified, improved to achieve the target RRF, thereby meeting the target SIL. So that is the point. I hope this is clear. Okay, friends? Right. In order to meet the target RRF, if SIF component architecture is modified, then SRS SRD shall be updated accordingly. So this is about the first part of the SRS, friends. I hope you had a very good insight on all these aspects related to the SRS, that is the purpose, scope, document layout, safety integrity level, SIF specification, description, common cause failure, safe state of the process, demand source, proof test interval, SIF response time, mission time, and target and achieve SIF. Okay. Thanks a lot for watching and of course your support. Okay. If you feel that this was useful, you can show your support, friends, by pressing the thumbs up and subscribe. And next, we'll continue this SRS and wherein we'll focus on the trip setting, manual shutdown process, trip state, reset type, maximum spurious trip rate, failure mode and SIS response, SIS startup and the restart requirements, SIS interface with DCS and FNG system, and software requirements, and also the maintenance override, MOS. All these we'll see in the SRS part 2. Okay, friends, thanks a lot. Bye-bye. Take care.